Hello everyone, welcome to this session titled Fiducial Market Tracking Using Machine Vision. My name is Saurabh. I am a principal consultant with Kavi Global. I've been with Kavi for about 5 years. Prior to that, I did a master's in industrial engineering from University of Wisconsin-Madison. Madison, by the way, is an amazing place. If you guys haven't been, especially in the summer, you should definitely visit it. Anyway, a little bit about Kavi. We are a service delivery company. We primarily provide technical and strategic solutions in different industry domains such as transportation, healthcare, manufacturing, among others. And we also have a couple of products of our own, one for data engineering and one for machine learning and advanced analytics. So my co-presenter, who unfortunately could not be here today, is Kazutaka Takahashi, who is a research assistant professor in the Department of Organismal Biology and Anatomy at University of Chicago. All right, firstly, before I get started, I just wanted to mention that I have deliberately refrained from making this presentation too technical, primarily because I wanted to cater it to a broader audience who are more interested probably in the overall approach rather than the nitty-gritties of the models and things like that. And secondly, if I do get into the nitty-gritties, probably a time of 25-30 minutes would not be enough. So just wanted to put that out there. If you're interested in a deeper dive or if you need any specifics, I'm happy to talk offline, and you're definitely more than welcome to reach out to either of us later. Right. Okay, so with that being said, let me jump into what are we going to talk about. So I'll just start with the motivation and goals of this study. Then the most of the time would be spent on the approach, and then at the end we'll look at the results and finally the next steps. So feeding, as we all know, is a highly complex and life-sustaining behavior that's essential for survival, basically of all species. And it is well known that certain neurological conditions, such as Parkinson's disease, ALS, and stroke, they affect our feeding behavior. So these conditions can cause a difficulty in chewing and swallowing, which is called dysphagia, and which affects the quality of life. So people can become frustrated or embarrassed and isolate themselves from public life. And also, more importantly, dysphagia can lead to malnutrition, dehydration, and aspiration, which is basically when food or liquid goes down the windpipe instead of the food pipe. And so basically feeding behavior or feeding behavior that affects a person negatively can result in more complex health issues. So the end goal of this study is to characterize feeding dynamics and gain insights into feeding behavior changes caused by these neurological conditions or by changes in oral environment. So this knowledge will enhance our understanding of the neural control of feeding behaviors in conditions of health as well as of disease. All right. So a little bit about the current state. So in this stage, the study is focused on rodents, that is rats. And high-speed X-ray videos of rats are recorded while they feed on kibble. The technique used to record the videos is called XROM, which stands for X-ray reconstruction of moving morphology. And these videos are recorded from 2 camera angles simultaneously. We have radio-opaque markers that are implanted in the head region of the rat, so in the skull, in the jaw, and a few markers in the tongue of the rats. And the goal is to track the movement of these markers across the video and quantify this movement at the end. But currently the tracking process is extremely tedious, as it is done using manual frame-by-frame method. So everyone pretty much has to manually detect each marker in every frame and then get the coordinates of those markers. This process, it consumes a lot of time, a lot of valuable time, and which further delays the more important research, which is basically characterizing or analyzing this feeding movement. So the immediate goal of this study, which is what we are focusing on today, is a near automated deep learning based solution for detecting and tracking the markers that would result in a much more faster, efficient, and robust process. At a high level, our overall approach looks like this. So first, we read the data, that is the raw videos, frame by frame, and we read them separately for the left and right cameras. And then we, after taking the raw data in, we use a neural network to generate a bounding box around the head of the rat. Since all the markers in the head, we don't really care about the rest of the video in this, or rest of the part of the screen in this case. So we do the neural network to build a bounding box around the head, and then within this region, we again use a neural network to detect the individual markers. So that's step 2. Then marker tracking is where we track the movement of each marker across the frames. So by tracking which marker is which across each frame. In this process, we use Kalman filtering along with the Hungarian algorithm, and I'll get into that later. Then after we track the markers, we need to do sequence matching, which is basically matching the tracks from the left and right cameras, so that we know we are comparing the same track in each camera. Finally, we combine the 2D track coordinates and we generate 3D coordinates for each of the frame, basically 3D marker coordinates for each frame. And that's what we'll be using in the next phase of this study to quantify and gain insights from the movement. All right, so the data we were working with, we have 13 pairs of videos, so 13 times 2, 26 videos, one for each angle, basically. I mean, for all the 13 videos, we have one for the left camera, one for the right camera. Each video is 720 by 1260 pixels, recorded at 250 frames per second. Each video is about 10 seconds long. And we have the head and marker coordinates per frame that have been manually generated, which are being used for training and evaluation. Each rat is implanted with about 18 to 20 markers, average of about 19 in each video. All right, so getting into each step individually. So the head and marker detector part. For the head and marker detector, we use TensorFlow's object detection API, which provides several out-of-the-box capabilities that makes it easy to construct, train, and deploy object detection models. TensorFlow provides several object detection models in its model zoo, as they call it. We use the SSD with MobileNet because it's easy to train and integrate for object detection type use cases. These are some key model parameters if you're interested. I would like to point out here that this approach may not be optimal, but we are rather looking at this as a kind of as a first stab. We plan to make further improvements to this solution as we work towards the goal. So the approach, the models used, or the model parameters may require a lot of tweaking as we go along, but this is just a good starting point is what we feel. These are the results of the head and marker detection. As you can see, in the left video is where we build the bounding box around the head, and even as the rat moves its head around, you can see the bounding box pretty well fits around the head. And then the right video shows each individual marker being tracked within the head region. All right, the next step is marker tracking, and where we have to track each individual marker across all frames. And this is a multi-object tracking problem. A multi-object tracking problem, especially like this one, where each object is essentially the same, since you can't really distinguish between one marker and the other. So this kind of tracking involves 3 steps. First is predicting the object location in the next frame. So trying to first predict where the particular marker would be in the next frame. Then is associating the predictions with the existing objects. And thirdly, we have track management, which is managing the lifespan of tracks. We'll now take a quick look at each of these steps individually. So prediction. For predicting marker locations, we use Kalman filter. Kalman filter, basically, it recursively uses the previous states of the object, such as position, velocity, and acceleration, to predict the immediate next position. This is a widely used technique in computer vision, but configuring the Kalman filter can be challenging. It usually requires a lot of trial and error to come up with the set of suitable parameters. Here we use a constant velocity model where we start with an initial estimate which then converges within a few frames of the video. All right. Then after prediction is association, where we need to assign which frame of the, basically, we need to assign which frame in the prediction corresponds to an actual frame, which marker in the prediction corresponds to an actual marker location in the next frame. So we do that by first computing the IOU, which is the intersection over union, for each pair of markers separately. So if we have 19 markers, for each marker we compute the IOU for each other marker. And so IOU is basically the, as I said, intersection over union, which is for the prediction and the actual location, what's the intersection of the 2 areas divided by what's the union of those 2 areas. So that gives us an idea of how well we have predicted the marker location. And so once we've calculated the IOU for each marker pair, we generate a cost matrix, and then we use a Hungarian algorithm to basically minimize the cost, or in this case, maximize the IOU. So that helps us assign labels to each marker across all frames, basically. Then is the track management. So in this particular case, track management is an important aspect of this problem, because for some frames, we might not get a detection based on a prediction. So we predict some value, but the actual location is nowhere close to that, so we miss out on that. So we get no assignment. If we don't get any assignment for a certain number of frames, we kind of declare the track as dead. Similarly, whenever we find a prediction for a new marker, we don't immediately start a new track, because that prediction or the match might just be noise. So to assign a prediction as a track, we wait a certain number of frames to gain enough confidence that these predictions are actually, this is a new track being generated. So in both these cases, you can see that we can have tracks die and new ones born during the course of the video. So what we need to do is we need to then, so basically we can end up with, we often end up with way more number of tracks than the markers. So at the end, we need to stitch all these tracklets together so that we have the same number of tracks as number of markers. And so the way we do it is by stitching, the way we do this stitching is by, for each dead track and for each new track, we look a certain number of frames forward and backwards to find the best match based on the Euclidean distance. Okay, so here we were talking about the 3 steps of the tracking process. Once we have done the tracking, now the next part is sequence matching, where, as I mentioned earlier, we need to, so we've generated, like, if we have 19 markers, we have 19 tracks for camera 1, and we have 19 tracks for camera 2. But now we need to tie them together so that track 1 in camera 1 and track 1 in camera 2 refer to the same marker, basically. So that's the part of sequence matching where so until now, we were basically generating tracks for each marker separately. This is where we combine them, not necessarily combine them, but we correlate them to make sure we're comparing apples to apples. We tried several methods for doing this, but the one that we went with was based on the frame-to-frame changes in the y coordinate of the marker. It seems like a pretty naive approach, but this was the one that gave us best results. Basically, we got an accuracy of 100% for the manually tracked data. Lastly, at the end of our approach, once we've correlated the markers from each camera, now we combine these readings, the 2-dimensional readings, together to get 3-dimensional coordinates. So this process is called triangulation, and besides the 2D coordinates of the markers, we also need some other information that pertains to the relative location of the 2 cameras, with respect to the distance between them and the rotation angle involved between them. So once we have all that information, we do this matrix multiplication basically to convert 2D to 3D. Quickly, let me just talk about a couple of evaluation metrics that we used. The first one is called percent IOU difference, which basically evaluates how well the tracking method worked. Here we calculate the total area in case of a perfect overlap, that is, if the predictions exactly match the actual locations for every frame in the video, then what would be the total overlap area, which is basically the area of each marker times the number of frames. Then we, for every frame, some of my notes are missing here. And then we calculate the percentage difference basically for between the perfect overlap area and the actual IOU. And the percent IOU difference ultimately tells us how well our tracking has worked or not. The second evaluation metric we used evaluates how accurately the tracks were labeled. So here for each frame, we determine the best matching marker label, and then for the entire length of the video, we calculate the percentage of frames having the same label as the overall track label assigned to that track. So the percent correctly labeled is another metric we can use to see how well our tracking worked. These are some of the results. As you can see in the video on the left, each marker is assigned a different color, which shows that it has been uniquely detected. And you can see that the color stays constant for most of the markers over the length of the video, showing that the markers were correctly tracked. Because if they weren't, then the colors would be jumping around. In the graph on the right, you can see that out of all the markers, the ones located in the head and the jaw region are much more accurately tracked than the ones in the tongue. So this result was kind of expected because the markers in the skull do not move much, and those in the jaw kind of move with a more or less regular motion or a periodic motion. Whereas the markers in the tongue move much more erratically because the tongue just does its own thing, and it's very difficult to predict markers or predict marker locations in the tongue. A few challenges in the approach. So the left image here shows the ideal scenario where you have the entire head of the rat in the field of view, and you can easily see each marker individually, and you can see it well because the contrast is good. But some of the problems we face is, one is the off-screen scenario, where if the rat kind of looks up or moves its head around too much, some of the markers may go out of the field of view, and we can then lose track of those markers. And sometimes when that marker comes back into the field of view, we may not be able to match that track effectively to before it went out of the field of view. Another scenario we face is occluded markers. So in one angle, you can have two markers clearly distinguishable, but if the rat turns its head, now both markers are facing the camera directly and they kind of overlap or occlude. So in that case, it can be, the tracks can go out of whack a little bit. So these kind of scenarios may negatively impact results, and we might need to find some corrective methods to handle these scenarios. All right, so some of the next steps we plan to do to improve the solution are to tune the marker and detection thresholds, marker assignment thresholds. Within the Kalman filter, we can tune the initialization velocities and try different models such as constant acceleration, play around with the covariance matrices. Then we can try also other nonlinear methods such as extended Kalman filter or particle filters. Within the marker detection, we are using currently the Hungarian algorithm, but we can try some of these other methods as well. And finally, in the track management part, for the stitching, we can further tune the parameters better to match disparate tracks to avoid incorrect stitching, so to say. All right, these are some of the references. Yep, and that's it. Thank you. As I said earlier, feel free to reach out to any of us later. And finished a bit sooner than I expected. So,
all right. How about a quick round of applause for Saurabh?
Any
questions? We have a few minutes here for questions.
Yeah. Okay. Hi there, thanks, great talk. A couple questions, if you don't mind. One question I had was, why didn't you use a phantom where you're using a physical simulation of the rat movement to compare the different algorithms that you were using?
That's a good question. I guess, yeah, I think this would be better answered by my colleague who's more on the neurological side. So, yeah,
fair enough.
I'll leave it for that.
The other question that I had is, what about doing overlap with some of the medical imaging algorithms like SURF on the another medium like video rather than just the radio video? So basically doing feature tracking with something like speeded up robust features and combining those data sets together to improve your performance on some of the more chaotic systems.
So could you repeat the initial part of the question?
Oh, sorry. The idea that I was talking about is doing essentially image fusion with both the radio and the video of the rat to try to improve and get feature sets both from the radio image and also from the actual video, like real video, with using an algorithm like SURF instead of just using the embedded markers.
Okay, yeah, that's a good question. So we've been also thinking about that, probably moving to a marker-less tracking as well, and that's something that we want to do eventually. So trying to focus on, other characteristics of the rat to do this. So, that would even simplify a lot of other things. So, like for even human subjects and things like that.
The final question that I had was around the embedded markers themselves. Do you think it makes an impact, especially on the tongue, where you're embedding the opaque markers into the tongue? Do you think it makes an impact on the actual natural movement of the tongue?
So good question again. Probably Kazutaka would answer it better, but from what I've heard, the markers are very light, and I mean, so I don't think it should significantly affect that.